Welcome back, everybody, to Algebra 1. This is Big Ideas, Lesson 7.5. Now, the good news about Lesson 7.5 is that we are kind of already used to what's going on with it. For those who do not have my class, we have been playing this game for about a month now, where I give you two numbers. We call this game the Combinator. So this is the Combinator. The Combinator works as follows. I tell you two numbers. Both of them are the combined versions of our two mystery numbers. So, for instance, I could give you the numbers 12 on top and 7 on bottom. On top, whatever number is on top, is what our two mystery numbers that we're trying to figure out multiply to make. On bottom, they add to make the number. So in other words, we're looking for two numbers that multiply to make 12 and add to make 7. Those who have my class may be very used to these type of problems and would have picked out that 3 and 4 work here. 3 plus 4 is 7. 3 times 4 is 12. This is going to be crucial for this lesson. Throughout all of Algebra 1, as soon as we've learned how to do something, we have learned how to undo it, or to do the opposite. So it should be no different after we learn how to FOIL to learn how to, well, unfoil. Let's say I have the following problem. I have x plus 8 times x plus 3. We know that when we have two binomials being multiplied, we can use FOIL to figure out what the product is. FOIL, as a reminder, is first, so we multiply the first two terms. X times x is x squared, so that's our f. Outer, we multiply the two outermost terms, x times 3, which is 3x, that's the O. Inner, we multiply our 8 times our x. 8 times x is 8x, so that's our inner. And last, 8 times 3 is 24. And we also know that whenever we do FOIL, there's going to be some kind of simplification we can do. So here in the middle, 3x plus 8x is 11x. So our final answer, after we multiply these two, is x squared plus 11x plus 24. We're used to this. But what if I gave you a polynomial in standard form, like the one below, and asked you to bring it back up to where we could FOIL it? In other words, to go from a trinomial in standard form and put it into two binomials in factored form. Well, that's going to be a little bit trickier. Let's say I have the following. X squared plus 5x plus 6. Let's try just experimenting with ways to work backwards, starting from x squared plus 5x plus 6 and ending up with two binomials. This is a little bit tough, right? Maybe it would help if we labeled each of these pieces, sort of like how we did up here. You see how we labeled the first one F for the first two terms? O is this, I is this, and L is this. Well, we can kind of label this the same way. Our first two terms, the ones that go here and here, multiply to make x squared. In the middle, we have our O and our I in combined form, and at the very end, we have our L, our last. So we know that whatever terms these are going to multiply to make 6. It's going to be a little bit tougher to figure out, because there's a lot of ways we can multiply to make 6. But let's start off simple. Do we know what two things multiply together to get x squared? Well, x squared is just x times x. This f is just x times x. So the first two terms must be x and x. Because when we FOIL and we do the first terms multiplying, that gives us our x squared. Okay, that's fine and dandy, but we've got some problems here. We don't know what will multiply together to get 6, and we don't know about this OI business either. That's the toughest part. You see, up here, when we combined like terms to get just 1, that's fine. But working backwards, it would be really nice if we knew which part of this was the O and which part of this was the I. Is this 5x, 2x, and 3x combined? Is it 1x and 4x? Is it negative 10x and 15x? We don't know. But we do know a little bit about our problem. Whatever these two terms will multiply to get will make 6. So let me give them some names. Let's call this term P and this term Q. So our FOILed version would be x plus something, I don't know, times x plus another something I still don't know. Well, we know a couple of interesting facts here. We know that P times Q, when we do our last part of FOIL, the L, what does that give us? Well, we said our L was 6, so we know that P times Q equals 6. What else do we know about our O and I, our outer and inner multiplications? Well, if we look and did an outside multiplication, x times q, we can write it as qx. So we know our O is going to be some number, q, times x. And if we do the inside terms, p times x we could write as px. And what do we know about qx and px? Qx is our outer terms, px is our inner terms. They combine to make 5x. In other words, we really know two facts. Whoops, let me erase that. We know that p times q is 6, and we also know that px plus qx is 5x. Let's take a look at this bottom problem here. Is there something I could take away from each of these three terms? Well, qx plus px equals 5x. Notice how we could divide both sides by x to get rid of it. If we divide out the x from both sides, the x here cancels out. We distribute the x across both of these. This would be qx plus px over x over x. The x's cancel out. In other words, we've just discovered that q plus p equals 5 by canceling out all these x's. We have a set of equations, kind of a system of equations, you might even say. We know that p times q equals 6, and we know that p plus q equals 5. Can we figure out, or at least brainstorm, what p and q should be? In other words, we're looking for numbers that multiply to make 6 and add to make 5. Wait a second. Doesn't that sound kind of familiar? This sounds exactly like the setup to a combinator problem. The number we're trying to multiply to make goes on top. The number we're trying to add to make goes on the bottom. Can we think of two numbers that multiply to make 6 and add to make 5? If you said 2 and 3, you're correct. So p could be 2 and q could be 3, or q could be 3 and p could be 2. Doesn't really matter which is which. The important thing is we've just found out what our two numbers are. P and Q are 2 and 3. So our final form of our answer is x plus, I'll say P is 2 and Q is 3. This should work out. But that was a lot of theorizing. I mean, look at all of this abstract, these literal equations we had here. It's a lot to deal with. Let's check and make sure it works again. So remember, we ended up starting off with x squared plus 5x equals 6, and getting down to x plus 2 times x plus 3. Let's see if we can work our way backwards and solve. If we wanted to FOIL these two terms, the first would be x squared, the outer would be 3x, the inner would be 2x, and the last would be 6. 3x plus 2x is 5x. We did it! We have successfully figured out how to factor x squared plus 5x plus 6. Now, what we did here was a proof of concept. This process here is exactly what people did all the way back in ancient times, when they first figured out how to factor these polynomials. I believe it was the Greeks who came up with this particular method. It was a long, thought-out process involving a lot of mystery variables. The good news is, since we've done so much combinator practice, we can kind of take a shortcut here. For instance, let's say we have c squared plus 11c plus 18. Again, we know that our final answer should look something like this. Something in parentheses. The good news is we can kind of take a bit of a shortcut here. I mean, shoot, we already showed that x squared is made by x and x. C squared is just made by c times c. Here is a tip for any future factoring of trinomials. If your first term is some variable squared, both of your first terms of your binomials are that variable. The only way to get c squared is from a c and another c, multiplying together. To figure out the last part, we kind of did a very long, roundabout way of doing it here in the notes, but let's take a look and see if we can use a shortcut. After all, in the last problem, all we really did was put the 6 on top and the 5 on bottom of a combinator. Our 6 was the last term in our trinomial, and the 5 came from this part of our middle term. So, let's do the same thing. Let's make ourselves a combinator. And in this combinator, the number at the very end, so the number that has no variables, the one that's all by itself, is always going to be what you multiply to make. So we're multiplying to make 18. And it makes sense too, right? This would be our last term in FOIL. It would be this mystery last term times this mystery last term. The plus 11, this positive 11, is what we wanted to add to make, because we would have some number here times c plus some other number here times c makes 11c. If you take out all the c's, what we're really saying is our mystery number plus another mystery number makes 11. So 11 will go on the bottom of our combinator. All we have to do now is figure out what goes on the sides. What are the answers to this combinator? What numbers multiply to make 18 and add to make 11? The numbers in question can only be 9 times 2 make 18, 9 plus 2 makes 11. So, this is positive 9, we write it out as c plus 9. This is a positive 2, we write it out as c plus 2. And this is our final answer. Let's do a weird one. let's do one that has a negative in it before we finish up the notes. In fact, you can find this problem in your own student journal on page 227. Again, we are going to flip to page 227, and I want you to try problem number 7. Try this one on your own. Remember what your combinator is made up of. Remember which term goes on top and which one goes on bottom. Pause the video here, try this out, and we'll talk about it in just a minute. Did you figure it out? Let's take a look together and see. So when we set up our combinator, again, the number that's all by itself goes on the top of our combinator, since we're multiplying to make that number happen. The number in the middle of the problem, we don't include the variable, goes on the bottom, since we're basically adding together our two mystery numbers to get that number. I might say, Mr. Strager, there are only so many things you can add together to make 3, and they never make 54. And if you said those exact words to me, you'd be right. But there is a pair of numbers that adds to make 3, that multiplies to make negative 54. Remember, whenever you have a negative product, two numbers multiplying to make a negative, it means one number is negative and one number is positive. So all we need to do is figure out what those two numbers are. And if you took a stab at this problem, you know that 54 can be factored as 9 times negative 6. 9 times negative 6 is negative 54. 9 plus negative 6 is just 3. So our answer here would be b plus 9, because again we have a positive 9, it goes right there. And here we have a negative 6, so we'd say b minus 6, or b plus negative 6. This would be the factored form. Alright, y'all. What I want to do now is this. We're going to flip over to the back side onto page 228, where we are presented with a bunch of problems here. We're going to work through number 15 together after you try it out on your own, but I'm also going to provide the answers to 13 through 18 so you can check your progress if you want the extra problems. For the last time doing these notes, please pause the video here, try out number 15, and if you want to, try out these other ones too. I'll be giving those answers as well. Alright, let's get started with problem number 15. And just a little disclaimer before we do, if you tried these problems down at the bottom, remember our skills from last section, where you have to move things over to the side to make it equal 0 first. So, for problem number 15, we have a polynomial that equals 0. And we're trying to figure out what w could be. Remember, in this form, we don't yet know how to find out what w could be. We can guess, we can try and check, but it would be much more productive to figure it out by putting it in factored form first. So, to put this in factored form, let's set up, you guessed it, another combinator. And we got to ask ourselves, what multiplies to make the last number, which is 10, what adds to make the middle number, negative 7? Ooh, now we have a positive product but a negative sum. That means we must be multiplying two negative numbers together. Negative 2 and negative 5 are those two numbers. And with some of these, you just have to guess and check, but you'll get better at spotting them as you go through. Negative 2 times negative 5 is positive 10. Negative 2 plus negative 5 is negative 7. So we've done it. We've factored our problem, but are we done? No, because unfortunately, we are asked to solve this equation, not just factor it. When you're asked to solve, you're looking for that equal sign. If the other side is 0, what did we learn last time that we could do? we could set each of these pieces, each factor equal to 0, and solve. In other words, we ask ourselves, what should w be here to make the whole thing 0? What should w be here to make the whole thing 0? So if w minus 2 equals 0, what should w be? To figure it out, let's get rid of this minus 2 by adding it to both sides, giving us w equals 2. And if w minus 5 equals 0, what can we do here? Let's add 5 to both sides to get rid of the minus. W equals 5. And these are your two answers. Thank you so much, everybody. I hope you have a fantastic day, and I will catch you next time in 7.6. Bye!